Today we're going to look at population dynamics and the importance of landscape connections. So we have already discussed population dynamics quite a bit, so I'm going to go quickly through some of those key elements, but focus in then how does it relate to animals moving across the landscape. So the most important part of long-term habitat management is looking at three things. We're looking at the habitat quality. We want to manage quality habitat for the long term. We need to have enough habitat, and those two need to go together. A little bit of quality habitat or a lot of poor quality habitat are both not going to work out long term for those populations. And then we need to look at the distribution of animals across the landscape. So this is going to tie back into our idea of generalist and specialist, but we can have generalist like a coyote that can live just about anywhere, and we'd call him a habitat generalist. He's perfectly suitable in town, in the periphery of urban areas, out in the agricultural land. He can deal with a lot of different types of habitat. And then we have our habitat specialists, like we've discussed. As an example, the black-footed ferret, who needs just prairie dog towns. Okay, so let's talk about how animals choose their habitat based on some basis of hierarchical selection. We have four things here, and we'll take a look at each of them. Geographic range, home range, how they use patches of habitat within their home range, and how they use resources within a patch. And so this idea of a patch is going to be really important here as we go through this today. Let's start off with geographic range. With geographic range, we're talking about groups of smaller subpopulations that contribute to a larger population. Subpopulations then can disappear and be recolonized by the metapopulation. So let's say we have several populations of a species, and it doesn't really matter what species. We could talk about any. Let's pick on the ferret since we've talked a lot about him. And we have these 7 little populations all in fairly close proximity to each other. We would call all of these subpopulations, but this entire area right here we would call the metapopulation. And the point here is that if one of these populations goes extinct for some reason, and extinct's the wrong word, is extirpated, disappears for whatever reason, but the habitat is still there, it's likely that members from these other populations may come in and fill that void at some point. And so therefore, the subpopulation, because it was part of that metapopulation, is likely to be refilled. So how does this relate to management? I'll bring this up in a moment, but if we get populations that are too far away, maybe way even out here, too far away from this metapopulation, then it's not as likely that if this population goes extinct that animals would refill it because they had to go so far or because of other reasons, which we'll get into today. So we need to consider the proximity of all of these smaller populations when we're managing for those metapopulations. What happens then, that blue one that I have out here, if you're not likely to get it recolonized, that would be what we call an island population. So a population that's not likely to be recolonized from the metapopulation should something happen to it and it go away. Okay, the next one then is home range. Home range refers to the area that that animal uses, or maybe a pair of animals uses, that provides the resources needed for survival and reproduction. It's its habitat, but it's the pieces of the habitat, it's the whole area, I should say, that that animal needs for survival and reproduction. So most often a home range is larger than a territory. The difference there is that a territory is something the animal will defend. The home range size will vary based on the size of the animal and the diet of the animal. So typically this is related to the trophic level of the animal. So an herbivore, an animal kind of as a primary consumer, is likely to have a much smaller home range than, let's say, a cougar that's a secondary consumer, and it would have a much larger home range. And size plays a role too. Regardless of trophic levels, our larger animals will have larger home ranges. They just need more food in order to get the biomass that they need. We talked about density dependence with our population dynamics lesson, and now we want to look at it in terms of how it affects habitat. So as a quick reminder, remember density dependence are factors that cause an increase in mortality or a decrease in reproduction when the population becomes more dense. So things like potentially disease, things like habitat degradation, things like that. Therefore, the number of individuals that the population can support is dependent upon the density of animals in that population. So if the population can support more when the density is less, then it would be density dependent. Density independent is when other factors play a role in mortality that are unrelated to density. Things like climatic factors, maybe floods in a fish population. There aren't too many examples really of density independent factors. So how does this relate to habitat? Well, I think this is a concept that you probably kind of intuitively know, but let's put some labels on it. So ideal free distribution is the idea that every animal, every individual in the population is free to choose the patch that will provide the most energy. And so they can settle anywhere. This would be the idea that I could choose any area of town to live in. That'd be ideal free distribution. But because of density dependence, at some point patches with higher resource value might end up getting higher densities of animals and therefore actually provide less value to an individual than patches with lower quality food. Let's talk about this in terms of human population for a minute, because I think we're in the perfect place to do this. So let's look at Fort Collins. Fort Collins was a nice little agricultural community that happened to be in a really nice spot. And so it's right next to the mountains, it's right next to the plains, it's easy to drive to and get in and out of Denver from. And so it grew in popularity, right? Everyone in the nation had the choice to come live in Fort Collins. Magazines reported it as the top 10 best places to live on earth. Well, so more and more people come here, and at some point it takes down the value of our town. Now, this is all my opinion, but if I have to wait 15 minutes to get 3 miles across town, then the value of this community has gone down in my mind because of the density of human beings. It's very similar with wildlife. So you had high quality habitat. Animals choose that habitat, but when more and more and more choose it, the value then may start to decline. Maybe they have more conflicts with each other, social conflicts. Maybe there's just more competition for that high quality habitat. And so what you may get then is animals actually choosing a lower quality habitat to avoid that high density of an animal population in the high density habitat. Okay, and then you also have, so that was ideal free distribution. This is ideal despotic distribution. This is where territoriality creates populations with lower than expected densities and high quality habitat. So you would expect that areas that have high quality would have high numbers of animals. Areas that have low numbers of animals, then you could assume that maybe they don't have that good of quality of food or of habitat. But because of this despotic distribution, that might mean that we have a few dominant animals in that area that don't let other animals in. And therefore, if we just did a population count and we got a low number, we might incorrectly assume that the habitat was poor. When the habitat might be good, they're just being kept out by the territorial animals that are protecting that area. Unfortunately, I can't think of any examples in the human world. I wouldn't mind if we could limit the growth of our population in Fort Collins. Maybe Boulder does it. I don't know. Okay, density dependence. with the source population. So now, because of this idea that habitat selection is a density dependent factor oftentimes, we have a couple other terms that are going to come into play here. A source population is generally that high quality habitat that allows animals to survive and reproduce. Animals have high fitness. It has enough resources for that population to survive, reproduce, and often expand. As that population expands, new individuals, often younger individuals, have to disperse to lower or to other habitats that may be lower quality. And those lower quality habitats might be called a sink population. So let's look at that. If I have a source population here, S-O-U-R, sorry, I can't draw with my mouse very well. Here's the source population. This is good quality habitat, okay? And as the density gets really high in here, they may disperse out of here because there's just too many, and they might disperse into this habitat, and we'll call this a sink population. So with the sink population, the animals are not necessarily surviving and reproducing. But if you were to look at this habitat at any one period of time, there would be a lot of individuals in here because the source is just filling it. It's kind of like, back to our bucket analogy with the limiting factors, this source population keeps adding water to the bucket, but there's a hole in the bottom. So mortality is high. I'm going to put an M in here for mortality. Mortality is high, natality is low, but the population may be equal to another area because it just keeps getting refilled through immigration rather than through natality. So densities of subordinate populations may be higher in sink populations. We could have a really high density of animals in those sink population, and if we just looked at one snapshot in time, we wouldn't get an accurate idea of what's really going on with habitat quality if we made that assumption again that high density equals good quality habitat. So a better way to look at quality of habitat is by looking at the animal's fitness. Remember, with fitness, their ability to survive, ability to reproduce. What affects survival? Quality of food. And we've looked at how we can have evidence of a poor quality habitat might be exemplified in the fat storage on the animal or the fats in their bone marrow. So we can look at these things, we could capture animals, we can evaluate their fitness, their health, and that's going to give us a better idea of quality. You could have 100 starving deer, or you could have 50 healthy animals. Which one do you think has better quality habitat? More animals or healthier animals? When we say it like that, it just makes a lot of sense. Okay, another quick review, natality and fecundity. Fecundity is the potential for young. So basically how many eggs can be produced or how often can they reproduce, but natality is the actual number being born. So how do we get differences? It would make sense that you're going to have the same offspring as you're able to have, but with some animals, and you read about this in your book, the potential for young might be there, but only be able to be fulfilled with high quality habitat. So let's take moose, for example. In low quality habitat, moose may either not reproduce at all, or they may produce only one calf per year. But in high quality habitat, they may actually produce twins and in some cases triplets. So if that cow moose is in really good health, her natality might equal out to her fecundity, the actual potential. But generally natality is much lower than fecundity. And our other way of getting animals in is through immigration, right? So we can add them through reproduction or we can add them through immigration. Now let's talk about that term recruitment, and we've already talked about it a little bit, but the number of individuals added to the population, the potential growth rates of a population then are dependent upon both the fecundity rates, what's your potential, and the potential for immigration. So we're going to move more to that potential for immigration. We've focused with recruitment so far as number of young and offspring added to the population that survive to adulthood to reproduce, right? But immigration adds to the recruitment as well, and we need to figure out what might prevent or encourage immigration into an area.